I thought this one was pretty easy, so I just went ahead and worked it ahead of time. A 55 kilogram hiker starts at an elevation of 1,600 meters and climbs to the top of a 3,100 meter peak. What is the hiker's change in potential energy? For this one, you're just using the equation that gravitational potential energy equals mgh. For the sake of simplicity, I call it his starting place position A and his final place position B. So the amount of energy that he gained going from A to B is we can just calculate how much he had at position A, calculate how much he had at position B, and then his change in energy was just the energy at position B minus the energy at position A, and we get about 800,000 joules. You also could have done it by just looking at the change in energy is mass times 9.8 times how much his height changed, right? How much higher he got, because really where he started makes no difference. All that matters is to go from here to here, he went up 1,500 feet. So you just do mass times 9.8 times 1,500, and it really doesn't matter. You get the same answer either way. Don't forget to throw units on your answer. A 17-kilogram child descends a slide 3.5 meters high and reaches the bottom with a speed of 2.5 meters per second. How much thermal energy was generated in the process? That word energy is in there, so you know we're going to hit some energy stuff. Let's just list what we have to begin things. So the mass is 17 kilograms, and the height is 3.5 meters, and the final velocity is 2.5. The energy transformation going on in this problem is at the top of the slide, you start with gravitational potential energy, and then that energy ends up getting spent in two ways. Some of it speeds the kid up as he goes down the slide, but the rest of it gets wasted as heat from friction on the way down. So from there, we can rewrite these energy ideas in terms of their formulas. So where there was gravitational potential energy, we can toss in an mgh and so forth for all this stuff. Then it's just a matter of plugging in the values for each one to figure out how much ended up over here as the leftover heat part. Once we got those equations down, it's really just a matter of throwing the numbers in. So this represents the gravitational energy. This is the kinetic energy. When you crunch them, it turns out that most of that energy got wasted in the form of heat. Some of it converted into Ke, but the majority of it went into this heat as he went down. So you ended up generating 530 joules of heat. 8 books, each 4.6 centimeters thick with mass 1.8 kilograms, lie flat on a table. How much work is required to stack them one on top of the other? I really like this problem, but before we do anything with it, centimeters, that stinks. So let's write that as meters. So 0.046 meters. Convert that stuff before you even bother opening up the problem. Let's jump in. First off, I'm going to look at this thing one book at a time and kind of work through it that way. And then halfway through, I'll see if there's some shortcuts, because what if we had this problem and we wanted to stack 100 books on top of each other or something like that? It would be cool to take a look at that mathematically. So what's happening here is you've got your first book chilling at the bottom, and you didn't have to use any energy on that one, so no energy for book number 1. For book number 2, the amount of energy that's required to put it up here is going to be mass times 9.8 times height, because you're giving it potential energy. So that's going to come out to, if you work it out, it turns out it takes about 0.81 joules to stack this book up here. I'm actually going to just put the value on the book itself. Now we come to the second book that we want to stack. And for this one, if you watch the bottom of the book has to increase in height by first 0.046 and then another 0.046. It's got to go twice as high up. Well, hopefully, with a little intuition, you guys know that the amount of energy that it'll take to lift it twice the amount is just going to be 1.62. If we lifted the same mass of book twice as high, then this one's going to be that amount. So I'm just going to kind of list this over here. So if we continue in this way, where every sequential stack ends up costing 0.81 more energy because you're lifting it 4 centimeters higher, then you get all these energies for each different book that you lift. And for the total energy over here, you just add all those numbers up, and I get 22 joules. Now, one thing that could have been a little shortcut on this is you could have recognized that they all had the same mg, and just the h's changed over here.